Hello all, welcome to online lecture series on Laplace transforms. In the last lecture, that is in lecture number 19, we defined a special function called Dirac delta function or unit impulse function and derived its Laplace transform. So here let us first recall the definition of this function and the Laplace transform of this function. So to define Dirac delta function, first we define the function delta epsilon of t minus a. It is equals to 1 by epsilon in the interval a to a plus epsilon, and at all other points it is 0. So here in this figure you can see in the strip a plus epsilon, its value is 1 by epsilon, and at all other places it is 0 here. So this is delta epsilon of t minus a. Now the Dirac delta function or unit impulse function is the limiting function of this delta epsilon as epsilon is tending to 0. So what happens if epsilon is tending to 0? Then this 1 by epsilon increases enormously. 1 by epsilon increases enormously and the width here decreases. So as the width decreases and the value of the function increases, that such a function is called as Dirac delta function or unit impulse function. It is called unit impulse function because always the area of this strip, always remains 1, whatever be the value of epsilon. As epsilon is tending to 0 also, the area of the strip remains 1. That is why it is called as unit impulse function. So now unit impulse function is delta of t minus a is limit epsilon tends to 0, delta epsilon of t minus a. So as epsilon goes to 0 here, 1 by epsilon in delta epsilon of t minus a goes to 0, goes to infinity, tends to infinity, and at all other places it is 0. And hence delta of t minus a is infinity when t is equals to a and 0 for t not equals to a. And moreover, we have the area of the strip, the area of delta of t minus a dt is always equals to 1. That is why it is called as unit impulse function. Because the area is 1, integral 0 to infinity delta of t minus a dt. This denotes the area of that strip. This is always 1. Now what is Laplace transform of this Dirac delta function? For that, first we derived Laplace transform of delta epsilon of t minus a, and taking limit on both sides, we obtained Laplace transform of delta of t minus a as e power minus as for a greater than or equal to 0. So remember, Laplace transform of delta of t minus a is e power minus as. Now let us find the Laplace transform of some functions which include this Dirac delta function. Before that, we have a small note here. What happens when a is equals to 0 to the Laplace transform of delta of t minus a? So when a is equals to 0, L of delta of t minus a is L of delta of t, and L of delta of t minus a is e power minus as, and a is 0 here, and hence e power 0 is 1. Therefore, L of delta of t is always equals to 1. Now let us proceed to problems. First one is evaluate Laplace transform of t square into u of t minus 1 plus delta of t minus 1. Here u of t minus 1 is unit step function and delta of t minus 1 is unit impulse function or Dirac delta function. So to find a Laplace transform of this function, first we use linear property of Laplace transform and we can write it as L of t square into u of t minus 1 plus L of delta of t minus 1. And we have L of delta of t minus a as e power minus as, and in the second term here in place of a we have 1. So e power minus s will be the Laplace transform of delta of t minus 1. So second term is very clear. But now let us look into the first term. We have t square into u of t minus 1. So here we can apply either second shift property for Laplace transform, or we can apply L of t power n into f of t property. We can use both the properties. If you want to use second shift property, express t square in terms of t minus 1 by subtracting and adding 1. But here I am using L of t power n into f of t property. What is L of t power n into f of t? L of t power n into f of t is minus 1 whole power n d power n by ds power n of L of f of t. Here, because we have t square, n is equal to 2, so we get d square by ds square of L of f of t. And as we have discussed earlier, L of delta of t minus 1 is e power minus s using this formula. So now coming to first term, L of t square into u of t minus 1 is d square by ds square of L of u of t minus 1. What is L of u of t minus 1? Laplace transform of unit step function. If you remember, we derived Laplace transform of unit step function as e power minus as by s. So L of u of t minus 1 is e power minus s by s. So now we have to differentiate this function e power minus s by s 2 times using the formula derivative of u by v. What is derivative of u by v? V into derivative of u minus u into derivative of v by v square. Here v is s in the denominator and u is e power minus s. So now let us apply that derivative formula. First, for the first time, if we differentiate, we get v into, that is s into derivative of u, that is derivative of e power minus s is e power minus s into derivative of a is 1 here, so into minus 1 minus derivative of s is 1 into e power minus s by s square plus e power minus s. So you can take minus common here because in both the terms we have minus. So minus is taken outside. So we have d by ds of s into e power minus s plus e power minus s by s square. Again let us apply u by v, derivative of u by v formula, which is v into derivative of u minus u into derivative of v by v square. So we get minus v into, that is s square into derivative of u, that is derivative of this term is s into derivative of e power minus s is e power minus s into minus 1 plus derivative of s is 1 into e power minus s. Here we have applied derivative of uv formula. Derivative of uv is u into derivative of v plus v into derivative of u plus derivative of e power minus s is e power minus s into minus 1 minus v into, u into v dash. This is u, v is s square, so its derivative is 2s divided by v square is s power 4. Now we can take s outside common in the numerator and that s can be cancelled with s power 4 in the denominator. So we get minus of s into minus e power s minus 2 into s e power s plus e power minus s by s cube plus e power minus s. Now by just simplifying this, we can write it as s square plus 2s plus 2 by s cube into e power minus s plus e power minus s. If we take out e power minus s common, that is s square plus 2s plus 2 by s cube plus 1 into e power minus s. Again simplifying, it is s cube plus s square plus 2s plus 2 by s cube into e power minus s. So this is the Laplace transform of the given function. Now let us see another problem. Evaluate Laplace transform of delta of t minus 2 by t, where delta is the Dirac delta function. So to evaluate the Laplace transform of this function, we can apply the property L of f of t by t. This is of the form L of f of t by t, where f of t is delta of t minus 2. What is L of f of t by t? It is integral s to infinity L of f of t ds. So now if in place of f of t we write delta of t minus 2. Therefore L of delta of t minus 2 is integral s to infinity L of delta of t minus 2 ds. What is Laplace of delta of t minus 2? Laplace transform of delta of t minus a is e power minus as. Therefore Laplace of delta of t minus 2 is e power minus 2s. So integral s to infinity e power minus 2s ds. What is integral of e power minus 2s? It is e power minus 2s by minus 2 within the limits s to infinity. If we apply the upper limit infinity, e power infinity is 0, minus lower limit is s, so minus e power minus 2s by 2. That gives e power minus 2s by 2. Next one is evaluate Laplace transform of sin h2t into delta of t minus 2, sine hyperbolic function. We know that sin hx is e power x minus e power minus x by 2. So sin h2t becomes e power 2t minus e power minus 2t by 2. Therefore sin h2t into delta of t minus 2 is e power 2t minus e power minus 2t by 2 into delta of t minus 2. We can take this 2 in the denominator outside and we can multiply e power 2t into delta of t minus 2 minus e power minus 2t into delta of t minus 2 and apply linear property to separate the Laplace transform. So we have 1 by 2 times Laplace transform of e power 2t into delta of t minus 2 minus Laplace transform of e power minus 2t into delta of t minus 2. So here we can apply one interesting property of Laplace transform. What is that? It is first shifting property, because this is of the form L of e power at into f of t. What is L of e power at into f of t? It is L of f of t with s replaced with s minus a. So here it is L of delta of t minus 2 with s replaced with s minus a is here 2, because we have e power 2t here, s minus 2. Whereas in the second term a is minus 2, therefore this is Laplace transform of delta of t minus 2, where s is replaced with s minus of minus 2, that is s plus 2. Therefore this is 1 by 2 times L of delta of t minus 2 is e power minus 2s. In the first term we replace s with s minus 2, and in the second term we replace s with s plus 2. So replacing we get 1 by 2 times e power minus 2 into s minus 2 minus e power minus 2 into s plus 2. That can be written as e power minus 2s. E power minus 2s is common in both the terms, so we can take it outside. We remain with e power minus 2 into minus 2, that is e power 4, minus e power minus 2 into plus 2, that is e power minus 4. So we have e power minus 2s into e power 4 minus e power minus 4 by 2. So this is of the form e power x minus e power minus x by 2. E power x minus e power minus x by 2 is sin h4. It's no t here, sorry, it is mistype here. This is sin h4 into e power minus 2s. Therefore Laplace transform of sin h2t into delta of t minus 2 is e power minus 2s into sin h4. No t here, please note that it is sin h4. Here is another one. Evaluate Laplace transform of integral s to infinity delta of t minus pi by 4 ds. So here is Laplace transform of integral. What is Laplace transform of integral s to infinity f of t ds? It is Laplace transform of f of t by s. One should remember the properties of Laplace transform to immediately apply for the given function. So here we use this property. In place of f of t, we have delta of t minus pi by 4. Therefore, Laplace transform of integral s to infinity delta of t minus pi by 4 ds is Laplace transform of delta of t minus pi by 4 by s. Just applying this formula. What is Laplace transform of delta of t minus pi by 4? It is e power minus pi by 4 into s, because Laplace transform of delta of t minus a is e power minus as by s. Therefore, Laplace transform of delta of t minus a is e power minus as. Here a is pi by 4. Therefore, this is e power minus pi by 4 s by s. So this is Laplace transform of the given function. Now you practice these questions. Evaluate the Laplace transform of these functions. T square into delta of t minus 3 plus delta of t minus 1 by 2. For the first term, you can apply L of t power n into f of t, and this is directly L of delta of t minus a. Again here we can apply first shift property for this function. And here first shift property as well as t into f of t, where f of t is delta of t minus 4. Okay, try to solve these problems. In case if you have any doubts, please contact me. Thank you for watching this video. Keep learning.